Go ahead.
So, hi everyone. We shall begin. So, Dr. Sushant Mahacham, did you say that okay? Yeah, thank you. Is a postdoc at the Hanson Experimental Physics Lab at Stanford. Is currently working with the HMI science team. He is also an active collaborator in the NASA Drive Center office and volunteers some of his time at the Wilcox Solar Observatory to keep it running. Sushant completed his PhD in 2019 from Georgia State University, and the topic of the dissertation was observational constraints on the solar dynamo and the hunt for precursors to solar flares. After the PhD, he spent 2 years on Maui as a postdoc at the Institute for Astronomy, and later moved to Stanford in 2022. Currently, Sushant analyzes helioseismic data to characterize the interactions between magnetic fields and plasma flows in solar interior. He has experience working on the development of feature tracking algorithms, numerical models of the solar dynamo, and preparing and utilizing machine learning ready datasets for forecasting solar flares. And with that, let's welcome Sushant, and you have the stage.
Thank you for that, and thank you to the organizers of the Colloquium and HAO for having me here in person. It's the first time I've traveled to give a Colloquium after COVID. So I'm really looking forward to interacting with many of you in a more relaxed setting than a conference or a meeting. This work I've done is over the last couple of years, and most of it was part of a NASA LWS project, which Marshall Deputy is involved in, and also affiliated with COFFEES, which is NASA side, the Drive Science Center, funded at Stanford University, but has collaborators all over. Its full form is the consequences of flows and fields in the interior and exterior of the sun. If you're interested in getting involved, we have several working groups, and we're always open for collaborations. Let me know, and I can put you in touch with the right kind of people. This work I've done with my first postdoc advisor, Zhudong, in Hawaii, and Junwei Zhao at Stanford University. And I'm going to talk about the influence of active regions on plasma flows inside the sun. So here's the two major plasma flows inside the sun. On the left is a differential rotation profile obtained from global helioseismology. The red dotted line here represents the Tycho line, or the boundary between the convection and radiation zone. Below that, the sun seems very, very close to a rigid body, but in the convection zone, that red dotted line, there's a high amount of latitudinal shear in rotation, as the sun rotates once about 25 days near the equator and once about 33 days near the poles. And when you have a superconducting plasma, as in the sun, in the presence of shearing flows, that's a recipe for magnetic phenomena, which powers the solar cycle. On the right is another flow pattern that's called the meridional flow, or some people call it meridional circulation. It is much weaker than the rotation rate of the sun. The amplitude is about 10 to 15 meters per second at the surface. And at the surface, the meridional flow goes from equator towards the poles, and it's supposed to return back towards the equator, although the depth at which this return flow operates is not clearly well known. And it's also not really well known whether it's a single cell of circulation or whether there are multiple cells stacked in depth and maybe even latitude. But we're not going to concern ourselves with the return flow in this talk. I'm just going to focus on the nearest to surface layers, wherein the meridional flow goes from equator towards the poles. So let's look at observations and how we understand the temporal variations in the meridional flow near the surface first. The meridional flow is important for surface flux transport on the sun. Sunspots on the sun typically emerge in pairs of oppositely oriented magnetic fields, and they typically follow the Hales polarity law and a typical drives a lot of tilt, although the scatter is in tilts is pretty large. And the configuration with which they emerge is kind of like, if at the beginning of the cycle, the polar fields you had were like blue in the northern hemisphere and orange in the southern hemisphere, representing positive and negative polarities of magnetic fields. The sunspots that will emerge if the sun is rotating from left to right in this image, the leading spot, which is ahead in the direction of rotation, would have the same polarity of magnetic field as the polar field in that hemisphere. And the following spot would have the opposite polarity. Now, over time, if you can create conditions such that you cancel some of the magnetic flux amongst the spots that are closer to the equator by cross-equatorial cancellation of flux, the same amount of net orange flux would be left over in the northern hemisphere here from this sunspot group. And that remaining magnetic flux after the decay of this sunspot region will be transported towards the poles by the meridional flow to help invert the polar field in that region. And over the course of an 11-year sunspot cycle, if you build up enough, if you transport enough orange flux here to the North Pole, it'll end up inverting the polar field, which will then be the precursor or the seed for the next cycle. So it is important to understand how meridional flow varies as a function of the sunspot cycle, because that it plays a dominant role in terms of deciding how much time it will take for us to transport the remnant magnetic flux in active regions to the poles. And it also plays a role in kind of deciding how much flux will remain after the cancellation of magnetic flux within the sunspot regions, because of things we'll discuss later. So for us to be able to predict how much polar field will build up near the end of the cycle, we need to understand how meridional flow varies as a function of the sunspot cycle. And people have looked at variations in meridional flow for the past 20 years. And from the general conclusion of the past year is that when you're measuring meridional flow, people usually exclude active region locations from the measurements of meridional flow, because active regions can change the meridional flow in their neighborhoods. And the general conclusion is the more aggressive you are in excluding active region neighborhoods, the less variation in meridional flow you measure. As in, if you exclude larger areas around active regions, you will measure an attenuated variation in meridional flow. Right? But there is still a lot of variation left after you exclude active regions. That's the general conclusion. And here's one example, very recent, COM et al. 2020. On the top is the meridional flow measurement as a function of latitude and time, like a butterfly diagram, in active regions, and in the bottom panel in quiet sun regions, so farther away from active regions. The white lines represent the centers of magnetic activity. And you can see there's a lot of variation in time in the active region. In the top panel, the amplitude of variation is about 10 meters per second, plus and minus. And in the bottom panel, in the quiet sun regions, the amplitude of variation away from the butterfly wings is about 5 meters per second. So there's like 50% of the variation still left after you exclude active regions, right? What do models say? The modelers have, and these are surface flux transport models, mostly. They have modeled meridional flow as a baseline meridional flow profile, which is like the orange curve here, function of latitude, just a simple sinusoidal curve. And on top of that, if you add inflows around active regions, which are observed in the seismic data, when active regions are present, they tend to drive flows inflows towards their flux centroids from all directions. So if you add inflows around the activity belt in the fashion of the lighter orange color here, which are proportional to the gradient of magnetic field, then you can create about 95%, recreate 95% of the observed variation in meridional flow. So the models are saying most of the variations in solar cycle scale variations in meridional flow are due to inflows around active regions, right? When you account for that, you account for 95% of the variation. What is left, so what they speculate is that the background meridional flow should be constant. And if you add on top of that inflows around active regions, that explains the variations in meridional flow. In observations, when you exclude active regions, you're still left with 50% of the variation. There's a discrepancy here, right? So who's right here is the question. And we decided to take another look at this. We thought let's pull on this thread of the general conclusion of the literature that as you aggressively mask active region locations, the variations in meridional flow attenuate. And people have seen attenuations up to 50%. We thought, well, what if we go farther? What if we exclude larger regions around the active regions? Can we get to the point where we agree with models that the background meridional flow is constant? So we used the time distance helioseismic measurements for this. This comes from the HMI time distance pipeline. What we have are velocity maps, as in north-south velocity, east-west velocity, and line of sight magnetic field, all spatially and temporally co-aligned, along with sharp metadata, which is the space weather HMI active region patches series, that gives us in these velocity maps where active regions are located, what is their area, what is their on-site flux, and some other parameters. The spatial resolution of this data set is incredible. It's 0.12 degrees heliographic, and the maps are available every 8 hours. If you want them for any reason, they're publicly available. And for this initial study, I only used the topmost layer available to us, 0 to 1 megameters in depth from the photosphere. So let's take this is a sample magnetogram in which you can see some active regions present. So we query the sharp metadata and we mark where active regions are present here. I'm showing a buffer distance of 5 degrees that is now excluded from these maps. We do this the same thing for the magnetogram, for the east-west velocity maps, which are just like this, and the north-south velocity maps, right? We're masking active regions in these maps. And the mask size here is 5 degrees. We've experimented from 5 degrees up to 30 degrees with successive increments of 5 degrees, right? But for visual representation, I'll only show the 5-degree masks here. We do this for one timestamp, because this map is in latitude and longitude. And since the map cadence is every 8 hours, we do this every 8 hours. And then you average over longitude, as well as average over a Carrington rotation in time. And then measure the meridional flow. On the left is a butterfly diagram of meridional flow variation. The color represents the meridional flow. The black lines mark the boundaries of the sunspot belt. And the leftmost figure is for a 0-degree buffer distance, as in I have not excluded any active region neighborhoods in creating this map. On the right of that is the meridional flow measured at least 5 degrees away from all active region centers. Yes.
Yeah, a few questions. First of all, how do you, maybe I missed this, but how do you determine the center of the active regions?
It's determined in the sharp pipeline. We get it from the sharp pipeline.
Okay, and then the other question is, for a single determination of the flow, how much time averaging is done?
Carrington rotation.
One Carrington rotation of the flow or of the, but to get the, you average the flow over a Carrington rotation, but to get the flow measurement itself, there's a time average.
Oh, that's 8 hours.
8 hours.
Okay. So on the left is the meridional flow pattern measured from everywhere. On the right of that is meridional flow pattern measured after exclusion of 5 degrees around active region centroids. Then we exclude 10 degrees in the next panel, exclude 15 degrees, 20 up to 25 degrees here, right? And as you exclude larger and larger areas, you do start to run out of data points. But what is interesting to note here is look at the variation, the solar cycle scale variation within the sunspot belt, right? It starts to diminish in amplitude as you go to 10 degrees, and when you're excluding 15 degrees around active regions, there is nearly no variation in with the sunspot cycle present in this region, right? So that is what the literature was hinting at. As you exclude larger and larger areas around active regions, the meridional flow variations attenuate in time. But if you exclude large enough areas, the variation kind of nearly goes away. But what's also visible is there is still some variation outside the activity belts in the quiet sun regions, which we'll discuss later. Here's what the time average profiles look like for meridional flow measured in different annuli around active regions. The darkest orange color plot here is the meridional flow measured within the first 5 degrees of an active region centroid. And then the lighter orange is the next 5 degrees, 5 to 10 degrees. And as you go to the brightest yellow colors, which represent meridional flow measured about 25 to 30 degrees away from active regions, it seems to converge onto this magenta meridional flow profile, which we think is the baseline meridional flow profile of the sun. And we calculated that baseline meridional flow profile as a profile in which we average all measurements that are at least 30 degrees away from all active regions and 48 hours away in time as well, because we excluded 48 hours, excluded regions within 48 hours prior to the first record of that active region, as well as 48 hours after the last record of that active region as well, because we didn't want to contaminate our background measurements with any pre-emergence or post-decay flows that are present. So it was just out of abundance of caution. Now, if we think this is the baseline meridional flow profile of the sun, we can subtract this and look at what's left. And here at the top is a residual meridional flow that is left over after you subtract the baseline profile. And what you can see in the sunspot latitudes now is predominantly the inflows, where red pattern represents flow that is pointing up, going towards the North Pole, and blue color is flow going down towards the South Pole. And so there's a convergence of these inflows towards the center of the sunspot belt. Okay. So that's majorly the solar cycle scale variation in meridional flow. But what's also evident is this quiet sun variation in meridional flow that kind of appears in between cycles. It originated in like late 2016, and it travels towards the lower latitudes and kind of seems to join the new pattern for the new cycle later. This is kind of similar to Bob Lehman and Scott McIntosh's extended solar cycle patterns, and actually it lies right on top of the coronal X-ray bright points. if you align them. And also is correlated with the torsional oscillation pattern.
Can I ask
Yeah.
I lost you there. Are you talking about the bottom or the top plot that's correlated with that?
Both of them show that quiet sun variation. This pattern that's shown by the magenta arrows.
Oh, you know what? I just can't see it. I'm gonna come closer.
Oh, yeah, the contrast is a little lower on this.
And that's a general slowdown that's behind the, underneath those.
It's
magenta
faster.
arrows. It's
It's a
faster.
little faster meridional flow, but that pattern is propagating towards the equator. And its amplitude is about 2 meters per second. So I've averaged that pattern here between these dashed lines in the year of 2017, 2018, and 2019, and plotted it here. You can see its peak is around 2 meters per second at around 40 degrees latitude in 2017. In 2018, it's about 35 degrees latitude, and in 2019, it reaches around 26, 27 degrees latitude. So it's a slightly faster than average meridional flow, and that pattern is propagating towards the equator, and it co-aligns very well with the torsional oscillation pattern and coronal X-ray bright lines. One of the interesting things is inflows around active regions is a dipolar signature or bipolar signature. It's a positive and negative thing. But this pattern that we see in the quiet sun variation of meridional flow, it's a unipolar signature in hemisphere. I mean, we only observe up to 60 degrees, so it could still be bipolar, and the other polarity could be very close to the poles. But as far as we can see, we only see it as a unipolar signature right now. So that characterization of this signal is something new that came about after we carefully constructed a baseline meridional flow profile from quiet sun and subtracted it.
Can I
So-
ask a question there?
Yeah.
Before that, so when we say the red is going to the north and the blue is to the equator,
Yeah.
so still these are unipolar?
Red flow here over the whole map is a positive velocity pointing north, and blue is pointing south. So yeah, in these localized regions, it is unipolar, but because it's an inflow, it's coming from both directions to pointing towards the same latitude. It's a bipolar signature. Right. So it looks like observations were kind of right in the general conclusion that the meridional flow variations attenuate as you mask active regions. But it's just that the extent of area around active regions that was excluded was generally up to 10 or 15 degrees around active regions. We needed to go farther, up to 30 degrees around active regions, to really see the effect of the inflows diminish and see a nearly constant background meridional flow of the sun. And the models were also kind of right that 95% of the variation in meridional flow comes from inflows, but there is still that the remaining 5% could be that quiet sun pattern, which is very weak. It's about 2 meters per second that we see in between two cycles. Okay, so now that we have a good handle on what the background flow profiles look like, we can go on and analyze what local to active regions flows look like, right? Here I've split all active regions into 3 different bins of unsigned flux. Sorry, cyan is really hard to see on the screen. I should have made a better color choice. Here are the low unsigned flux active regions, medium and high unsigned flux active regions. Unsigned flux is essentially a parameter that correlates with the area or the size of the active regions. And on the left column is the average magnetogram. In the middle column is the averaged east-west velocity, which represents inflows. And in the right column is the average north-south velocity, which again represents another component of inflows. And you can see that the larger the active region, the larger the area, the extent of its influence on flows around its blood center. Right? Now, to inform surface flux transport models and dynamo models, we wanted to come up with a function, an analytical function that you can fit as a function of the size of the active region, which can create synthetic inflow profiles that conform with the data. Right? So what we did was, first, there are some issues with just fitting these inflow measurements. As in, one thing that you can notice is the high latitude branch of inflows here in the northern hemisphere is very well formed. It's coherent. It's of the same sign. But the low latitude branch of inflows is kind of broken up here, right? When the southern hemisphere was stronger in activity, it affected the low latitude branch of inflows here. And so we made an assumption that this must be due to the contamination of these inflows due to the stronger activity in the southern hemisphere. So we made a choice to only fit the high latitude component of inflows around active regions, and then assume that the inflows are 360 degrees symmetric around the active regions. And we will try to see how good our assumption is by validating it later. The second choice, so here are the assumptions that we made. First, inflows are 360 degrees symmetric around active region centroid. The low latitude inflow branch is weaker and kind of breaks up sometimes when you have cross equator flow driven by stronger activity in the other hemisphere. And that inflow magnitude only varies with unsigned flux, which is essentially the size of active regions. This is the most dominant factor that we could find. Any dependence of inflow magnitudes on the tilt of active regions or the bipolar separation or other stuff is secondary to the unsigned flux of the active regions. So we just decided to go with that. And then we will try and see how good our assumptions are later. So here are what our inflow fits yielded. We decided to fit a function that kind of looks like the first derivative of a Gaussian function and gives you profiles that look like this on the left. We split all the active regions into 9 different bins of unsigned flux, going from 10 to the power 20 Maxwells up to close to 10 to the power 23 Maxwells. And for each bin in unsigned flux, we fit the inflow speed around those active regions. The largest active regions have inflows that are designated by the darkest orange color here. And as you go to brightest yellow, you're looking at the smallest bin in unsigned flux. Okay. So there is a variation in amplitude with the size of the active regions. The greater the size, the larger the amplitude, as well as variation in the extent up to which their influence, the influence flows in their neighborhood.
But hold on, real quick.
Yeah.
Is it a nonlinear relationship between the size of the active regions and the peak inflow amplitude? Like it looks like on your left plot, it looks like about a factor of 2 difference. What was the difference in the sort of size and the factor of 2 difference in the inflow speed? But I'm guessing the size range of the active regions is larger than that.
Yeah, so the size here is on a logarithmic scale.
Yeah.
And the speed is on a linear scale here. So yeah, if you plot in linear units, it will not be linear.
Okay.
All right. So now that we have fits to the inflow profiles, let's see how good our assumptions were. And the assumptions were that inflows are 360 degrees symmetric around active region centroids. If that is true, then by creating synthetic velocity maps, we should be able to reproduce the weaker low latitude inflow belt out of contamination from the other hemisphere. The low latitude inflow branch is weak due to cross flow. We should be able to reproduce that. And we only chose unsigned flux as the parameter with which inflows vary. So we'll see how good those assumptions are, right? Here are the inflow fits. Now, to create synthetic velocity maps, use these fits to our inflows, and then we create a blank velocity map with latitude and longitude, just like in the data, but zeros everywhere. And you can query the Sharp database again, which tells you where active regions are located at what times. It says, okay, active regions are there, and there. And it also gives you what was the unsigned flux in those active regions. So according to that, you can look up the inflow profile fit and put in the inflows corresponding to the sizes of the active regions in that synthetic map, right? And just like the original data, which had a cadence of 8 hours, we do this every 8 hours for the whole period of the SDO mission. And you can do the same thing again. You can do this every time step, an average in longitude and over a Carrington rotation, just like we average the data, except it's not data now, it's a synthetic inflow profiles only, right?
There's what are the red and blue color table of that? The arrows are showing inflows.
The arrows are inflows and the colors of the magnetograms, yeah, the average magnetograms. But so this synthetic averaging we do for the velocity maps only, we're not averaging magnetograms here. Okay, so here's what our reconstructions look like. On the left is the residual periodal flow that was observed after baseline periodal flow was subtracted. And on the right is a reconstructed map of residual periodal flow by only considering inflows around active regions, right? And you can see it kind of reproduces a coherent high latitude branch, but a broken up and weaker low latitude branch of inflows, which is what we kind of expected when the southern hemisphere is more active. And because the inflows can stretch up to 30 degrees away, they can weaken this low latitude inflow belt in the other hemisphere. Because these active regions are going to pull flows towards themselves, and they will essentially drive a cross equatorial flow towards the southern hemisphere. The other thing you can see is that the correlation between these two is 0.78. So I guess the assumption that we made that inflows vary with the unsigned flux of active regions is kind of good enough as a first for a first try. We can definitely be fine-tuned later by finding the dependence on the tilt angles of active regions or any other parameters. And yeah, so the only thing that cannot reproduce by inflows is the quiet sun changes in meridional flow that appear in between cycles, which are not related to the inflows, so we don't expect to reproduce them anyway. So it looks like our assumptions are kind of good enough for a first try, and so we have these inflow fits for active regions now, which can be ingested into surface flux transport or dynamo models.
Ask another question. So, I mean, you've got your active region and the inflow is all pointing in towards the middle, but you end up with things which are essentially, you end up with just the stuff pointing north-south. Is it because the meridional flow is kind of pulling that apart, but the east-west part of that has just canceled itself?
Yes. That's one of the things that I'll cover. Okay. One of the other things that you can do is you can average look for cross equatorial flow now. If you average the residual meridional flow within 5 degrees of the equator in both of these plots, in the observed as well as the reconstructed meridional flow, you can look at how the cross equatorial flow depends on hemispheric asymmetry in sunspot number. And here's on the top the observed and the modeled cross-equatorial flow. And at the bottom, you have the hemispheric sunspot numbers, where the color shading is magenta. The northern hemisphere was dominant, and so it pulled stronger inflows across the equator, which resulted in a positive cross-equatorial flow towards the northern hemisphere. When the southern hemisphere was dominant, it pulled inflows across the equator into the southern hemisphere, and so you end up with a negative cross-equatorial flow. And then the northern hemisphere is dominant again. You have a positive cross-equatorial flow. Now, cross-equatorial flow is really important because it's the net magnetic flux emerging in a bipolar magnetic region theoretically should be net zero, right? Because you have equal amount of positive and negative flux. And the amount of magnetic flux that you can cancel across the equator then creates a net flux in that hemisphere of the opposite sign, which can be transported to the poles, right? So it's the amount of polar flux buildup that you have during the cycle, you have to have the same amount of cross-equatorial cancellation of flux. So, and cross-equatorial cancellation of flux can be enhanced by cross-equatorial flows. So they can play a major role in deciding how much flux is canceled across the equator, and the same amount of opposite polarity flux should reach the poles as well, right? So you can monitor the buildup of polar flux from two ends, kind of. And the effect that these cross-equatorial flows actually have on surface flux transport models and dynamo models is not really well explored. We don't really know how much of an effect they can have. They should have a significant effect, but we haven't characterized that well yet. Because most models force the meridional flow to be zero at the equator. Right? So that is one thing that we should be exploring. So here are the questions that we've answered so far. The variations in near surface meridional flow explained by active region inflows, yes, mostly. But there is also evidence for changing background meridional flow, which occurs in the quiet sun regions. The east-west inflows do not contribute to the torsional oscillation pattern. This is a preview for the slide upcoming. What the spatial extent of active region inflows is a little larger than we expected, can stretch up to 30 degrees. Does the spatial extent of inflows vary? Yes, it varies with the size of the active regions, which is kind of expected. The smaller the active region, the less spatial extent it will have in the flows that it perturbs. And which active region property affects or is correlated with the inflows the most is the unsigned flux of the active region. Now, this was all about meridional flow. Let's look at how they influence differential rotation of the sun, how active regions influence the rotation rate of the sun. Now, here's the inflow diagram again. In the middle panel are the east-west inflows. And as you'd expect, they mostly seem to probably cancel out. Let's look at their variation as a function of distance away from active regions. So these are averaged east-west flows in different annuli around active regions. And they don't seem to vary with distance away from active regions at all, which was a little surprising to us in the beginning, because meridional flow varies so much with distance away from active regions. We expected the rotation rate to also vary with distance away from active regions. But it kind of makes sense if you think from a two-dimensional perspective that the east-west flows should cancel and have no net effect on the rotation rate at sunspot latitudes. But this does go against Hank-Sprout's theory of the origin of torsional oscillation. On the left, again, we have the variation of meridional flow as a function of distance away from active regions, and compare that to the variation of rotation rate as a function of distance away from active regions, which is like really minimal. There isn't much variation at all, but there is a lot of variation in meridional flow. What this is telling us is that the variations in meridional flow, they have an origin that is spatiotemporally linked to the locations of active regions. And because the amplitude of variations is decreasing farther away from active regions, it naturally leads you to the conclusion that these variations are driven close to active regions. But for torsional oscillation or the variations in differential rotation, that seems to be a phenomenon that is omnipresent on the sun. It doesn't vary in amplitude or phase farther away from active regions. It's the same magnitude and phase whether you're looking close to active regions or far away, right? So these two seem to be spatiotemporally unlinked from each other. But if you plot the torsional oscillation pattern, which is bands of slightly faster or slower than average rotation rate of the sun, on top of the residual meridional flow map. So the background colors here, the blue and the red, are the residual meridional flow as we've seen before. On top of that, I've plotted contours of the torsional oscillation pattern. So the magenta contours here, I hope you can see that. Yeah. The magenta contours here are the band of slightly faster than average rotation of the sun. And the green contours represent bands of slightly slower than average rotation of the sun. And you can see the faster than average rotation bands coincide really well with the low latitude inflow belt into the active regions, right? Which has led Roger Ulrich to a paper that was, I think, just published yesterday to think that they are the same thing. The variations in differential rotation and variations in meridional flow are two components of the same phenomenon. And so we should collectively call them torsional oscillation is what he's proposing. But I disagree with that because this plot is created after you average over longitudes and you average over every Carrington rotation, right? But if you look at a more granular level as a function of distance away from active regions, these two things are not spatiotemporally linked. The variations in meridional flow are driven close to active regions, whereas the torsional oscillation pattern, the differences in rotation rate are not. They're omnipresent everywhere. If they were the same thing, two components of the same thing, you should have seen a variation in the amplitude of a torsional oscillation as a function of distance away from active regions as well. So what then explains the high latitude, the quiet sun variation of the quiet sun meridional flow, and what explains this correlation without probably causation of the torsional oscillation and inflow profiles? I don't really know, but I can utilize the most powerful tool known to astrophysicists, which is speculation, and highly biased speculation because this comes out of something related to my PhD thesis. I think that the torsional oscillation pattern originates deep inside the sun as a consequence of the magnetic field amplification processes. And so it is correlated to the locations of sunspots at the surface. And when sunspots emerge at the surface, they kind of undergo this enhanced cooling effect, which drives inflows into the sunspot latitudes, right? So both the inflows and the torsional oscillation pattern are related to the sunspot locations. Might not be directly related. But because torsional oscillation originates deep inside the sun, or if torsional oscillation originates deep inside the sun, in the magnetic field amplification process, by the time it shows up at the surface, it would be really mixed around in longitude, right? It would not be spatially, temporally co-located with the location of the sunspot's surface per se. It should be more mixed around, which is probably why we don't see the dependence of amplitude of torsional oscillation as a function of distance away from active regions. But we see that in Medrone flows because the variations, the inflows in Medrone flow, they're driven at the surface. Because of that. That's my speculation for that. Thank you. This is a QR code to refer. This QR code just covers the first third of the talk. Yeah. The next 2/3 is unpublished yet.
Thank you very much. That is an interesting and insightful talk. And do people have questions? Both online and offline, Sarah?
Two questions.
Yes.
Great. Also, a bunch of questions, but the two questions are, you can address them however you want and how deeply you want. One of them has to do with the asymmetries and the flows across the equator. And is there any reason the sun can't just getting more and more asymmetric and get completely out of balance? Is that what's the kind of restoring thing going on there? And then the second question is, how does this all relate to the presence of low latitude coronal holes in your mind?
Latitude coronal.
You can take the first one first, maybe.
Yeah. The first one, I was actually thinking about that on the flight over, as to what would be like. There must be some kind of a nonlinear quenching thing that goes on, right? If you have hemispheric asymmetry, it should drive cross-equatorial flows, and that should hopefully result in the next cycle being more symmetric, probably, which is what we see, by the way. The last cycle, so this is cycle 24, which was highly asymmetric, and the next cycle, cycle 25 currently, in which each hemisphere of the current cycle is weaker than cycle 24, but the overall amplitude of the current cycle is higher because they are so synchronized, right? So last cycle was highly asymmetric, and the current cycle is very symmetric in activity. So I would speculate that there is a kind of a quenching mechanism, as in hemispheric asymmetry should drive cross-equatorial flows, which would lead to the next cycle being more symmetric instead of a runaway asymmetry. But I'm not sure about the mechanism, which is why I said, like, this is really not well explored from the surface flux transport models and dynamic models point of view. And we need to introduce these into the models and then see what actually leads to that quenching, if it does lead to quenching. Second question about the coronal holes. Equatorial coronal holes. I don't know a lot about coronal holes to be able to really have a strong opinion on that. But the coronal holes usually correspond to unipolar patches, right? Predominantly unipolar fields connected where they connect to the photosphere.
Yeah, the reason I asked, I don't know if Ian wants to chime in, but your patterns look a lot like our low latitude coronal holes Macintosh archive maps.
Oh, which one? These ones?
No, the residue ones, the real faint ones, but not the active region,
Okay.
right?
Oh, these ones you're saying?
Yeah.
The ones in the quiet sun.
Do they, Ian? If I got it back?
Yeah, I'm here. So I think I was glad Sarah asked this. I think what she's getting at is there are theories that low latitude coronal holes in some case originate from active regions that have decayed, and the stronger sign is left, and then you end up sort of with a coronal hole in a unipolar region. So maybe it's that the other polarity is balancing out across the equator, but that you get the unipolar region due to the canceling out of the two and being left with just one polarity. That makes
Yeah,
sense.
but there's definitely, and I maybe low latitude's the wrong, I mean the non-polar. And some of them are
Non-polar.
actually, some of them are actually more like mid-latitudes and
Okay.
actually have patterns that show up in the, yeah. And so anyway, I think we should look at this.
It would be really interesting to do because like we can, I mean, if there is a good, I'm not aware of the databases of coronal holes, but if we have a good database that can mark the locations of coronal holes, we can run it through the same pipeline and analyze flows and other things as a function of distance away from coronal holes instead of actually.
And we do. And
Yeah, we do.
We'll talk, we'll talk.
Sure.
We'll talk. Cool.
More questions?
Did you find with the cross meridian flows any correlation with renegade sunspots that have the violate the Hale's polarity rule?
As in the link between cross-equatorial flow
Yeah.
and the animal spots, kind of the ones with inverted polarities. I did analyze the magnitude of inflows as a function of the tilts of active regions. I guess when you go across 90 degrees, you're actually looking at anti-Hale regions, right? We didn't particularly see a huge difference between the inflow profiles for anti-Hale spots and normal polarity spots. And I think that's kind of conforms with the understanding that inflows are driven by enhanced cooling around sunspot regions, and that enhanced cooling is there regardless of the orientation of the polarities, right? So we don't particularly see any difference in measurable difference in the inflow profiles, whether the active region is in Hale or anti-Hale configuration. And based on that, I would not expect it to alter the cross-equatorial flow in any different fashion because the inflows behave the same.
Do you see any effect of the Coriolis force on these inflows? Is there some rotational flow around spots you
There
can
is a
pull
little bit
out?
of vorticity, and one of the most interesting things was, I didn't discuss it here, but when we were calculating the baseline measurement flow, we excluded 48 hours prior to the first record of the active region and 48 hours after the first record of the active region as well, right? So I separately analyzed those 48 hours prior to the first record of that active region. And when I average flow profiles in there, I see small vertical flows centered around the expected location of active region. So there is a little bit of vorticity, and that is one thing that we're thinking about, because right now inflows, because assume they're 360-degree symmetric, they only have a divergence, they don't have a curve. That's another thing that we should characterize and include as a second order correction.
Yeah, I agree that you should look at that because that vorticity itself will have a torsional oscillation signature because it will have a non-zero longitudinal average.
Right.
And I was going to ask, I'm trying to understand that your 360-degree symmetric profile, how does that jive with the other plot that you had that showed a big difference between the meridional inflow versus the zonal inflow? So you're saying the meridional inflow extends like 30 degrees away, but the zonal one does not. So
The zonal one also does extend that way,
okay.
But so both these plots are velocity versus latitude, right?
Okay.
Because the inflows in the direction of rotation extend over longitude, when you average over the longitude, the east-west inflows cancel,
Okay.
leading to no net effect in the change of rotation. Right?
Yeah, but it could. If there's a vorticity present, then it won't cancel.
Yeah,
Yeah.
but this is still from measurements. These are not from
Right.
synthetic.
Well, I'm
velocities.
saying that when you look at it more closely, you might be able to tease out a signature from that the
Maybe.
Globally, it doesn't show much influence on the torsional oscillation, but there might be something more subtle in there.
Right, there might be, but like Matthias knows this better because he's modeled it. But Hank Sprout's theory of like explaining torsion oscillation using invoking Coriolis force acting on the inflows,
Yeah.
wouldn't that predict that you get a similar amplitude of variation in torsion oscillation here as a function of distance away from active regions as you do with Merton's law? Or would it be this different?
I mean, that depends how all these individual flows around active regions, how they close globally, right? If the east-west components, if it is just a local rotational flow, or as Mark said, I mean, there is a axisymmetric component in there, which adds to the torsion oscillations.
But even if it is there, why don't we see it when we average over active regions? It's one of the things that was surprising to us.
It would be interesting if you kind of pull out these rotation azimuthal component and it has that the 360-degree symmetry. Is it just the flow circling around, or do you mostly see flows east-west above and below the active region belt where you have the torsion oscillations? What's really the symmetry of that flow?
So one of the things is what we're analyzing here is so in this one, only the differential rotation profile was subtracted. I didn't subtract the torsion oscillation profile, which is why you see those bumps. That is the oscillation that is visible here. So this itself might be representing the vorticity, right? This is the torsional oscillation pattern created by probably by that vorticity. But the question is, why does it not vary with distance away from active regions?
I mean,
If it is driven by active regions.
It's me being a devil's advocate and saying something. Again, I am purely playing a devil's advocate here. And when you're saying that there's no impact on the differential rotation, that it doesn't vary with the distance from an active region. Typically, when I see a bunch of points and they say, well, this bunch of points are not correlated with, with the distance, I would expect to see a spread that has equal probability of being above and below the zero. And such as what I see on the differential rotation plot here between 40 and 60, I see spread of points above and below zero. But I do not see that spread of points above and below zero evenly anywhere between -40 and, let's say, +20.
Okay. So most of the things that stick out of this cluster, that's all this 0 to 5 degree layer, which we know there is sunspots rotate at slightly different speeds because the expectation is that they're anchored at deeper layers, and the sunspots rotate at a slightly different rate than the rest of the photosphere of the sun. So all of the things that are sticking out here are correspond to that 0 to 5 degree annulus. Anything above that, it's all like really the same. They're all on top of each other.
But this is for a particular time. Where's the active region built at this?
This is averaged over the rising phase, the first 3 years of the cycle, and the
Okay.
active region belt is in the middle of this, so around 20 degrees latitude,
Right.
around here.
So it'd be interesting to investigate that a little more, because if
Yeah.
you take an inflow and it takes a figure skater pulling in her arms, the
Mhm.
farther she pulls them in, the faster she spins, right? So if you just take a converging flow around an active region and compute the vertical vorticity profile that arises from that, it's probably going to peak closer to the active region and it's 30 degrees out, right? I don't know. There could be a signature in there, but it'd be interesting to look at it more.
Yeah, we can try and calculate that. We have created a database of very well isolated active regions where we can go in and look at that.
We are running slightly over time. I propose to carry out the subsequent discussion offline. Yeah, I'm just checking for the chat one last time. Okay, so let's take the speaker again. And again, stop the recording.